So in the last 15 years, there have been two really huge developments, one completely experimental and one completely theoretical. The experimental development was the observation in the late 1990s that the universe is, of course, is expanding, which we've known for a long time, but that in the recent history of the universe, recent meaning the last few billion years, the expansion rate, instead of slowing down, has been speeding up again. So the universe is actually accelerating. This is an astonishing discovery. It was rewarded with a very richly deserved Nobel Prize this year. That single observation completely transformed the way many people think about fundamental physics. It's not difficult to explain why the universe is accelerating. It's a very simple addition to our normal laws of physics in order to accommodate it. But the problem isn't that we don't know how to make the universe accelerate. It's that by all rights, the universe should be accelerating at a vastly, vastly larger rate than it appears to be. And it's an incredible paradox and a mystery why it's accelerating so slowly, why the acceleration rate is as small as it turns out to be. And observing it, that it is accelerating, focused a lot of attention of theoretical physicists on this problem. And we certainly don't have a resolution yet, but it's probably one of the deepest questions that we've had to focus on for a long time anyway. And we are all forced to think about it because of this experimental discovery. So that's by far the most important experimental discovery of the last 15 years. The most important theoretical discovery of the last 15 years, which also happened in the late 1990s, is that the two sort of pillars of 20th century theoretical physics, quantum mechanics, well, all of physics really, but which impacts our thinking in theoretical physics on all the time. The laws of quantum mechanics on the one hand and of relativity on the other hand. These two theoretical frameworks have been challenging to reconcile for a long time. And there's been a lot of progress in the 20th century in reconciling some of them. The laws of special relativity and of quantum mechanics, it is possible to put them together in a common rubric, in a common framework. On the other hand, relativity, which tells us that space and time are different aspects of the same thing, was further generalized to the notion that space and time can also curve and bend, and that's associated with gravity. Bringing gravity into a common framework with the other picture has proven to be much more challenging. It proved to be so challenging that for a long time people thought that these two ideas, the ideas of really quantum mechanics and special relativity on the one hand, and of gravity and this generalization of relativity on the other hand, general relativity on the other hand, were in violent conflict with each other. An astonishing discovery of the late 1990s was that when thought of appropriately, not only are they not in conflict with each other, but they're actually two different descriptions of one entity. This is a kind of answer that no one anticipated, even though people have been wondering about this question for decades. No one anticipated that the resolution would be not that we had to combine this structure and that structure to one bigger structure, but that in fact there were two complementary descriptions of one underlying thing. And both of these developments, both the experimental and the theoretical development, as people have been thinking about their implications in the intervening decade, both of them are making it completely clear that the next big development, and the one that many people are working on different aspects of and trying to push towards, is going to have to involve some kind of really radical transformation of our idea of what space and time are. We've seen aspects of this transformation already in the theoretical developments. We've been forced to think about more radical versions of them in order to make sense of the experimental developments associated with the accelerating universe. And I don't know how long it'll take for the next real breakthrough to happen, but there was some feeling of ferment, that there was something up. At any rate, the questions that are involved are very, very big ones. And it is possible to attack them in concrete ways and sort of feel like you're making some small progress on them at any time. So that's where I see the future of the subject going. I think it's been clear to many people for a long time. You know, it's been clear to theoretical physicists for decades now that the idea of space-time isn't fundamental. That space-time is doomed as a fundamental notion, and it has to be replaced by something else. That general fact has been clear. Maybe it's clearer and clearer now, but it's certainly clear to many people even 20 or 30 years ago. The really new thing that started in the last decade, but is sort of accelerating from more and more directions, is that there are ways of attacking this problem, that there are ways of making progress on it. It's not a permanent philosophical thing that stays out there in the ether without ever, well, I guess there is no ether, but stays out there in the land of dreams without ever going anywhere. We have a variety of angles of attack on this problem. A variety of theoretical angles of attack on this problem. So that's what I see as a sort of real grand challenge of the 21st century, is to make some progress on this question. At the same time, in this decade in particular, we have some really spectacular experiments. We have the Large Hadron Collider. There are some experiments, astrophysics and cosmology experiments, that are going to give us a lot more actual data about the world. And they're certainly not guaranteed to tell us everything about these mysteries, but they can give us important clues to keep pushing us in the right direction. So it's a particularly special time, I think, even just this decade. There are theoretically these questions that are sitting there, and I suspect are going to dominate our thinking for 10 or 20 years. But in this decade, we have not only that, but we also have prospects of some exciting data that might really surprise us, which would even be more wonderful. Or it could confirm that some of the basic directions and ideas that we've been thinking of are roughly on the right track. That would be very nice. But at any rate, this confluence of having hints from experiment as well as wonderful theoretical problems to work on is really unique. It's definitely the most exciting decade, at least to me so far in my own career. So hopefully we'll have something really solid and exciting and important to say by 2020.